Okay, let's take a look at the graphs of sine and cosine functions in this lecture. I have graphed one cycle of each of these functions. The one on the left is the cosine function, and the way this works is you can plot points, and I assume again, because this is a pre-calculus course, that you all have seen these graphs before, so I left out the details on plotting points to graph these. But you could certainly plot points. For example, let x be 0 and then do cosine 0 is 1. You get 1 point. Let x be pi over 2. Cosine of 90, pi over 2, 90 degrees is zeros, and so on and so forth. What's important is when we graph these sine and cosine waves, for each of these, we use 5 points. These are 5 key points that we use. For cosine, the key points are at 0, pi over 2, pi, 3 pi over 2, and 2 pi. Okay, and these are, by the way, the points we have exact values for, so that's why we choose them. And they also show the key points on the graph. For the graph of sine, the key points that we plot are 0, pi over 2, pi, 3 pi over 2, and 2 pi. At pi over 2 and 3 pi over 2, we're going to see the peak and the valley of the graph. And for the others, we're going to look at the x-intercepts or the zeros of the function. Okay. Now, the graphs of sine and cosine, by the way, are called sinusoidal. Namely because we can write one in terms of the others. For instance, sine, the graph of sine is a shifted cosine that is shifted to the right, pi over 2. So if you shift, remember this is a horizontal shift in the x minus h form, f at x minus h form of the function. So h represents a horizontal shift to the right of pi over 2 of cosine, and you get exactly what sine is. And just to kind of show you here, here's pi over 2, and you can kind of see, and there you go, that would be now the cosine x that's shifted to the right, pi over 2. And because of that, again, we call these sinusoidal graphs. Okay. And there you go. Let me put the word. It's sinusoidal. That means everything could be viewed in terms of sine. All right. Having said that, what I want to do actually is now I'm going to graph other variations of sine and cosine. Again, you may have seen these done before, but I want to show you how I actually graph these functions, or variations of them, I should say, rather quickly to see if this is how you've done them, or at least give you an alternative to graph in these. Now, the general form of sine and cosine waves that we're looking at in this section are in the form of a sine. I'm using the author's notation of omega. That's what this is. This is omega. X plus b. Okay, and here omega is positive. And the other one is a cosine of omega x plus b. All right, and in both cases here, omega is positive. If omega is negative, then we get a negative inside parentheses, and we can use the even oddness properties of sine cosine to rewrite these using negative angle identities. I'll show you an example in a moment. But for both sine and cosine in the general form, the period for both of these is given by 2 pi over omega. That would be the period. The amplitude of this, the graph of the function, which is in general the high minus low point divided by 2. Absolute value of a is called the amplitude for sine and cosine. Okay, and again, in general, if you do high minus low divided by 2, you get the amplitude for any graph. And again, we're going with absolute value of a because a could be negative. If a is negative, then that will cause a reflection of the graph about the x-axis. So absolute value of that, the amplitude, will not change even if you reflect the graph about the x-axis. Okay, so we got the amplitude and the period. The important other points are the zeros. The zeros of these functions. Remember, the zeros are the x-intercepts of the graph of the function. So the zeros of sine in the basic form is given by k pi, where k is integer. Okay, and remember, integers are -3, -2, -1, 0, 1, 2, 3, and so forth. Okay, those are the integer values for sine. For cosine, the zeros of cosine are at pi over 2 plus k pi. These we need to know. And the best way to know them is, again, to either go to your unit circle or look at the graphs. For instance, for sine, again, zeros are at 0, pi, 2 pi. So hopefully that will everyone will be able to remember the k pi from that. But again, you can go to the unit circle and look at these on the unit circle like we did before. And there you have it. Now the effect of B here, B is going to be a vertical shift. Vertical shift of the basic sine and cosine function. If B is positive, the shift is up. If B is negative, the shift is down. In my examples, I don't have anything with a vertical shift, and that's just for simplicity. Okay, so let's go through and do some of these examples. So for instance, let's say I want to graph the function -1/7 of cosine of 7/2 x. Okay, something like this. Now, I want to emphasize on the fact that we don't, or I personally don't plot points. So again, if you're doing something like this, choosing values of x, finding corresponding y's, and then plotting points like this, then you're not doing this the way we should be doing. Okay, that's not the idea of how we do these in pre-calculus and beyond. So for this one, first of all, let's do the amplitude. Amplitude is absolute value of -1/7 or 1/7, which is a rather small number, right? Close to 0. But that's what the amplitude is. What is a period? The period is 2 pi over 7/2. Invert and multiply the denominator, we get 4 pi over 7. So we are able to identify the amplitude and the period. Now, if I want to graph this function, by the way, here's how I would graph this function. First of all, the negative in front of 1/7. This negative tells me there is a reflection about the x-axis, correct? So here's how I'm going to do it. The amplitude is 1/7. So what I do in case of a cosine is I'm going to set 7/2 x between 0 and 2 pi. Okay, why 0, 2 pi? Because that's what I have, a full cycle. There you go. One cycle of the graph of cosine. So I want to know where is 0 now and where is 2 pi. Multiply everything in this inequality, all parts, by 2/7. 0 times 2/7 is 0. There you go. 2/7 times 0. And then I'm doing 2/7 times 7/2 x. And then 2 pi times 2/7. So I'm multiplying all parts by a positive number, 2/7, which I don't have to change the direction of inequality, but notice how that will allow me to isolate x. So what used to happen, a wave from 0 to 2 pi, now happens from 0 to 4 pi over 7. And check out how I'm going to graph this thing. So I'm going to actually graph my cosine wave. Right, just like I did. Remember before it was 0, 2 pi? Check out what I'm going to do. I'm going to call starting point 0. The complete cycle occurs at 4 pi over 7, and there you go. From 0 to 4 pi over 7. The trough, the low point, happens at halfway between 0 and 4 pi 7. So 1/2 of 4 pi 7 is where the low point is. Okay, and that'll give me 2 pi over 7, doesn't it? So there you go. That's the coordinates of this point. This is 2 pi over 7. See how easy that was? Okay, and of course the amplitude is 1/7, so I'm going to call that 1/7, this negative 1/7. So my graph is done, and there you have it. Except I need to reflect it now, right? So I'm going to do that. That's going to be the last thing I do. So the trough, the low point, now becomes the high point. So it's going to look like so. It's going to go like this. And then the other portions, they're going to go like so. The blue curve is the actual graph of this function. And I can get the x-intercept rather easily as well, right? This point and this point. How do I find those points? Well, this point is halfway between 0 and 2 pi over 7. So I go half of 2 pi over 7. That's pi over 7. So that's the x-intercept. The x-intercept, this point, is at pi over 7. So it looks like my tick marks are pi over 7, 2 pi over 7, 3 pi over 7, 4 pi over 7, like that. The other intercept is at 3 pi over 7. And there you have it. The complete graph without plotting points. And notice how I graphed it and then I just let the coordinate system accommodate for my graph. So this is how I personally do them. I like him doing this way because I can do them really fast and without plotting a single point. Let's take a look at the graph of negative 2x. So this time there's negative inside parentheses, right? What I'm going to do is recall the negative angle identity for sine. Sine of negative theta is negative sine of theta. Okay, so I'm going to write this as negative sine of 2x. So whatever the graph of sine 2x is, in the end, I'm going to remember to reflect it. And that's the final graph. All right, so let's do actual sine of 2x now. Like before, for the graph of sine, I'm going to set 2x, what's in parentheses, between 0 and 2 pi, where I got one complete graph of sine, this graph. So I want to know where's my starting point and where's my ending point now. Okay. Divide everything in this inequality by 2 and I get x lying between 0 and pi. The period, actually the length of this interval is the period of this function. The period seems to be pi. Or you can do period as a formula, 2 pi over 2 and you get pi. Remember 2, that's the number, that's your omega in the general form. Now, perfect. So I'm going to have a sine wave. I'm going to have a sine wave from 0 to pi, correct? So this is what I'm going to do. I'm going to actually graph my sine wave there. And then I'm going to let the coordinate system accommodate for it. Except remember, my sine wave is going to be a dotted wave. True, because that's not the final graph. I do need to reflect it, correct? So I'm going to do this in a dotted form. There. That's a 0, and then the ending point is not 2 pi, but pi for this new function. And so there you go. That's the graph. You see how simple that was? Half a is going to be pi over 2. There. And those are the x-intercepts. Now, how do I actually graph the actual function with a negative? I'm just going to reflect this. So that's this part. And there's the other part. Reflected. And that is the final graph of this function. You see how that works? Now, the other way we could have done this is using reflection about... Oh, and by the way, let me show you another cycle of this for what I'm about to talk. This would be the other part, right? If I continue the wave. Now I can talk about the reflection, about the y-axis. So this is it. We're done with this graph. Now, we can also think of this as f of ax, right? Where f of x is just sine x. F of ax, now that would be f of negative 2x, which makes it sine of negative 2x, right? I can view sine of negative 2x this way. Now, in this form, a is negative 2, which is less than 0, so the consequence is a reflection, WRTO, with respect to the y-axis, correct? So I could have graphed it this way. And what does that mean? Well, if I graph y equals sine 2x, remember my sine 2x, my dotted curve, this one that was dotted, that's my sine 2x. This is sine 2x. The effect of negative 2 is to reflect it about the y-axis, right? So it's actually going to look like this. And there you have that portion of the graph. Sorry. There. These are the reflections that you're looking at across the y-axis. Now look at this wave, look at this wave. They look the same. You see that? So a couple of different ways we can think of it, however you like it. The first way I did it is my favorite way, but you can do it another way as well. All right, let's take a look at another example. In this other example, suppose I want to graph y is equal to 9/5 cosine of negative 3 pi over 2x. So again, here's how I'm going to work this, because cosine is even function. That means cosine of negative theta is equal to cosine theta. So the negative actually isn't going to affect the graph here. The negative that's inside parentheses for this reason. Therefore, I'm just going to graph this as if it's 9/5 cosine of 3 pi over 2x. You see that? How I eliminated the negative due to negative identity for cosine. Now this is easier to graph, isn't it? So just like before, I want to know where is 0 and where's 2 pi. 3 pi over 2x, set it between 0 and 2 pi. Multiply everything by 2/3 pi. You get 0. That's the reciprocal of 3 pi over 2. So I want to isolate x. That's what it takes to isolate x. So I'm going to multiply 2 pi times 2 divided by 3 pi. The reciprocal of 3 pi over 2. Okay. This is going to give me 4 pi. Oh, the pi's cancel actually. So it gives me 4/3. There's no pi there. So it's going to be just 4/3. Okay. Now, I can graph this one again. This will tell me this is the start of the graph and this is the end of my graph. So what am I going to do? I'm just going to graph and this is a cosine, right? So I'm just going to graph my cosine wave. There, that's my cosine wave. And the amplitude is 9/5, call that 9/5. You see how I graph and I accommodate the graph with the coordinate system, not the other way around. The starting point is 0, the ending point is 4/3. The trough, which is the halfway mark, right in here, that's the trough. Sorry. No problem, we can create them easily. This was the trough. There. Then it bent and curved like this. So the halfway mark is going to be halfway of the distance from 0 to 4/3 is 4/3. So it's half of 4/3. That's 2/3, isn't it? There you go. The trough, the low point is at when x is 2/3. What about the x-intercepts? Okay, well, from 0 to 2/3, half of that, right? So it's going to be half of 2/3 at 1/3. So this is 1/3. It looks like my tick marks, each tick mark is 1/3. So I go 1/3, 2/3. This should be 3/3, right? Which is 1. and then next one is 4/3. And of course we start at 0. So those are the 5 key points that I needed. And there you're looking at the graph of this wave. Okay, not bad, huh? Quickly and without plotting any points. All right, let's take a look at one more for this section. We will be doing more of the graph of sine cosine near the end of this chapter, which will be like in 2 sections when we talk about phase shifts, and then I can kind of bring it all together with a phase shift. That's the only thing that we haven't done yet. So we have the amplitude and we have the period. Now this time sine. First of all, the period, by the way, the period P is 2 pi over its absolute value of omega. Absolute value, because see, it can be negative. I'm going to drop my x out, sorry. Without an x, that's just a constant. Okay, there you go. So my period is going to be 2 pi over absolute value of negative 2 pi over 3. And invert and multiply, we get 3. Right? Well, let me put the detail. That's 2 pi over 2 pi in the bottom, 3 on top. That's invert and multiply 2 pi over 3. Let go of negative because we're taking the absolute value, and those cancel. So that's just 3. The period of this function, the graph of the function, is 3. That means you have one complete cycle in an interval that's 3 units long. Okay. Now, and what else? Period and amplitude. Amplitude is going to be 5/3. That's if the question asks for that. Now let me graph this one. Again, like before, for sine and cosine, I set the content. Oh, negative, negative, negative. Hold on. So I'm going to change this using negative angle identity to sine 2 pi thirds x. Okay. Again, what happens is in the end, I'm going to reflect the graph about the x-axis. Now I can set 2 pi over 3 x between 0 and 2 pi to see where is my starting and ending now. I'm going to multiply all parts by reciprocal of 2 pi over 3, which is 3 over 2 pi. I'm going to multiply all parts by this. Okay, now 0 times any non-zero is, the 0 times anything, any real number is 0. So that's just 0. 2 pi thirds times its reciprocal is 1. Therefore, inside, between the two inequalities, I just have x. And the 2 pi's here across, and that's 3. Now, if you look at this interval, by the way, the length of the interval is the period, which we found earlier. You see that period? We found it to be 3. It's going to be exactly the same thing. Now, I just need to graph this thing, don't I? And here's how I'm going to graph this. Again, all I need to know is where is one cycle, and for us the one cycle is from 0 to 2 pi, which is now shifted or changed from 0 to 3. So I'm actually going to graph my sine. There you go, like that. It's dotted because I want to do the reflection about the x-axis, the last thing I want to do. This is 0, and here's my ending is 3. Notice my graph is already done. I'm just accommodating for the graph through my coordinate system. The amplitude of this graph is going to be what? Absolute value of negative 5/3 or 5/3. We found that here already. See, I'm going to label my y 5/3, and there you go. That's good. What else? Oh, the peaks and the valleys, we can get those easily. Now, halfway between 0 and 3, that's 3 halves, isn't it? And halfway between 0 and 3 halves is half of 3 halves, or 3/4. That pretty much establishes the tick marks. Every tick mark here on the x-axis is 3/4. So I got 3/4 and then 3/2. That's 3/4 plus 3/4. And then you add 3/2 and 3/4 to get the next key point here. Remember, we need 5 points. 1, 2, 3, 4, 5. The 0, 3/2, and 3 gives you the x-intercepts. The 3/4 and this other number we're about to find, which is 6 plus 3/4, 9/4. This 9/4 is going to be where the trough of the current graph is, but for the final graph, that's going to be the maximum. So I'm ready now to finish this. And the negative in front, that means I'm going to reflect. So here we have that part, and we have this part of the graph of the function. Now this is the complete graph. See how that worked? Oops, sorry, that one is a little crazy. This is better. Again, I'm just doing one cycle. That's all I'm doing. I know the function is periodic, so there you go. It just goes like that. But we don't care about these other parts. I just want from 0 to 3. And there you have it, the peak and the valleys. So the peak happens at 9/4, comma 5/3. You see, I'm just reading it from the XY coordinate. And this one, the trough is at when x is 3/4, the y is negative 5/3. I graphed it, and I'm just managing to plot points on top of the graph the way we explained it. All right, so there you have it. Quick lecture for this one. Now again, we'll do more of these graphs, but this is how I'm going to graph, by the way, all of the other functions in the next section. We're going to look at the graphs of the remaining 4 trig functions next. So we are done with this lecture, and again, as always, thank you for watching.